Everybody, let's spend a little bit of time talking about the pH scale and what it means and what it does. So when you do this, we need to keep in mind that there are several definitions of acids and bases. And then I'm actually going to show you the list of strong acids and bases coming up in the next slide. I'm not going to say anything really about them other than you just need to memorize them. It's really the only thing that you can do. I don't have any fancy mnemonic device or anything that tells you what they are. It's just I don't know. It's just what you have to do. But one of the things that you have to realize, and this is this point right here is something that people forget, and basically pH really only tells you how concentrated the hydrogen ions are, or the hydronium ions are, and it doesn't tell you whether the acid is strong or weak. There's a list of strong and weak here. Okay, so strong and weak means something completely different than pH and it's the concentration of the hydrogen ion. Okay, well, for the purposes of this video, it does. Okay, so here are the strong acids and the strong bases. I don't know why strong bases is way over there, but there it is. And you're going to have to memorize these guys, okay? HCl, HBr, HI, N, HNO3, H2SO4, HClO3, and HClO4. And then all the group 1 hydroxides are the strong bases. I guess I can, make it so it's not as confusing. So these are the bases, and the group 1 hydroxides are things like lithium hydroxide, and then sodium hydroxide, rubidium hydroxide, potassium hydroxide, so all of those. And then there's barium hydroxide, strontium hydroxide, and calcium hydroxide. So what is a strong base or a strong acid? It is one that completely ionizes in a solution. So something like lithium hydroxide is completely soluble, LiOH, when it is aqueous, when it is in water, it's only found as lithium ions and hydroxide ions. Okay, and that's what makes it strong. The same thing with hydrochloric acid. When hydrochloric acid is in water, it's only found as chloride ions and hydrogen ions. Actually, let me take a minute. It's actually hydronium ions, because water, remember, water can act as an acid or a base. So water plus H2O, okay, is going to give us H3O plus. So it's this guy, and this is called the hydronium ion. Maybe that's something to write down and keep a hold of for a while. But the hydronium ion, and that's synonymous really with the hydrogen ion, or this proton here. But nonetheless, here's the list of strong acids and bases. But what is pH? Okay, well, the pH scale is probably something that you may have come in contact before, or something about. And so the beauty of the pH scale, or one of the things about the pH scale, is that it's a log scale. So that means every number is 10 times different than the number previous to it. Okay, so pure water has a pH of 7, because remember, water can undergo hydrogen. It's going nuts. Okay, water is amphoteric and gives off the same number of hydrogen ions as hydroxide ions, so they're still present, hydrogen ion, hydroxide ions, but they cancel each other out. So 7 is in the middle. Okay, and then you look at some of the examples. Battery acid, really strong. Drain cleaner, really strong. Oh, notice what I'm saying. I'm saying they're strong. I don't want to say they're strong. It's just that they're very concentrated. Okay, they may be strong, and it turns out that battery acid is some combination of sulfuric acid, and lead and zinc and all sorts of things to make it really, really potent and powerful. But it is also a strong acid because it completely ionizes. Okay, and here's HCl from the stomach lining. Again, HCl, strong acid, but it also is very concentrated. Okay, up here, ammonia, something that we don't necessarily think about all the time as being a base, is a base, and it's a fairly concentrated one. We can get ammonia to get to be 11, sometimes 12 on the pH scale, and that's pretty powerful, but this is not a strong base by any stretch of the imagination. So, anyways, I'm sure you have some familiarity there with this, but let's move forward. Okay, and so here is water being amphoteric, and here's some of the math behind this. I'm not going to go into this math. So what we should take from this is that the pH of water is 7.0, and this gives us the formula of pH right here as being the negative log of the concentration of hydrogen ion. And keep in mind that I use hydrogen ion and hydronium ion interchangeably so that we can figure this out. Okay. So, as we move forward, one of the things that we should do is keep in mind that if we're going to calculate the pH of a strong acid, we're going to use this formula right here. pH is negative log of hydronium ion, and remember the previous slide I used hydrogen ion. Whatever, it's fine. And then we can use an ICE chart to figure out how much H3O plus is given off. Okay, and then you find the pH because we have the ending amount of H3O plus. Now, turns out that we don't necessarily need to use an ICE chart, but I am going to use an ICE chart to begin with, and then you'll see why we don't in the future. So let's look at this problem, and I will do this like I said we were. Okay, and so I'm going to go HCl plus, watch this, H2O. I'm going to do something funny. Okay, reacts to form H3O plus Cl minus. Okay, so now this is our ICE chart, and I'm going to use molarity in mine. So this is 6 molar. In water, there's so much water that we're not even worried about it. So now, HCl, what do we know about strong acids? They completely ionize. So this goes to 0, so we lose 6 molar here. And now this concentration here, we started with 0, but we gained 6 molar. So at the end here, we have 6 molar H+. The idea is that typically the ratio of strong acid to the hydronium ion is 1:1. So the concentration of the acid is typically the concentration of the hydronium ion. So let me pull up my calculator and let me show you exactly how to calculate the pH of this acid. So I'm going to go here. I'm actually going to erase this, and I'm going to call this up again. So now let's just do this. Okay, so pH is equal to the negative log of the concentration of the hydronium ion, or the hydrogen ion, whichever one you want to use, it's fine with me. But we know that this is a strong acid, so because it's a strong acid, we know that the concentration of the acid is the concentration of the hydronium ion, so it's negative log of 6. I can put the 0.0 here, and so now we do negative log of 6. We put that right in our calculator, and for some reason I am not focused. I don't have a focus here. But the answer then becomes negative 0.77. And this introduces kind of an interesting thing, is because the pH scale can actually go negative. 7 is the middle, and that's really the only boundary that we have here, is that the pH is 0, is a fictitious boundary that we've made up in the past. Okay, and so it's really just 7, and then it can expand out either way. Okay, so now let's talk about this. This is strong acid. This is perchloric acid. So we know that the pH equals the negative log of the concentration of the hydronium ion, H3O plus. And so again, for this one, we do the same thing. So we do negative log of 0.0003, and we hit enter. And now for this one, we can see that the pH is equal to 3.52. Okay. Again, the pH doesn't tell you anything about its strength. Both of these are strong. It just tells you which one is more potent. This is the one that you don't want to handle with bare hands because it is more concentrated. Okay, it's not that it's stronger. Okay, so that was way too long, but regardless, that's the introduction to the pH scale and how we calculate the pH of a strong acid.